think about data-driven machine learning more generally beyond reinforcement learning, right? So how has it evolved? Um, the the initial forays into this perhaps were supervised, right? So you have supervised examples, you have images and labels of cats or dogs or airplanes or houses, right? And then you train big neural networks to go from those images to the classification or go from those images to regression. So you have supervised learning. And data driven machine learning was in supervised land for a long time, maybe until like 2017, 2018, and then we started to shift a bit further into unsupervised land. So unsupervised land is you don't have the labels, and then you just have exercise, and then how do you learn from some unsupervised objectives? So some examples of unsupervised objectives are contrastive learning, or things like sequence modeling, right? So a lot of the generative AI methods you think about now are in some ways unsupervised learning methods, right? And so these are still methods for supervised learning. They're not methods for sequential decision making, right? So, but we kind of want to follow this pattern. I think when machine learning started being really successful as a data driven method, we started moving from things that were purely supervised to things that were more unsupervised, right? And so, um, what I want to ask today is how do we develop methods for unsupervised reinforcement learning and or unsupervised decision making, right? So if we think about what unsupervised decision making might look like, it's basically going to be something like this, right? You start with a large corpus of transitions. Let's say they're, transitions of states, actions, next states, or observations, actions, next observations. So things that look like this large droid data set over here. And these are like collected without a particular task in mind. You collect a large unsupervised data set, and then at deployment time, you kind of adapt behavior to a specific problem, right? So you want to do something in the printer, you want to put the napkins in the trash, you want to turn on the light switch, right? Each of those are different downstream problems that you might care about. And so an unsupervised RL method, in my opinion, is going to start from a large corpus of these transitions and then kind of adapt itself to any one specific problem instance. And so just like unsupervised RL right now, you can kind of think of as like if you think of like GPT-2 and so on, right? They trained unsupervised and then you adapt it quickly to any one specific problem. Um, and you kind of want to take a similar view on decision making. You want to start from a something that you learn from a large corpus of these unlabeled transitions, and then you transition over to adaptation to deployment time very quickly. So given that premise, the question that I think is important to think about is what can we even learn from this data, right? So, when we talk about reinforcement learning, typically we're talking about like reward maximization. Right? We're talking about things like policy grading. We're talking about things like Q learning, things that are trying to maximize the reward for a particular problem. But now if I have a large unsupervised corpus of data, what do I even learn from this data, right? Um, and if I think about the MDP formulation, right, I've given you access to the transition dynamics, but I haven't given you access to anything else. And so, kind of the direct conclusion here is that if you give me a large corpus of unsupervised interactions, the right thing to do is to model the dynamics of the world, right? So, it's model how the world transitions from one state or one observation to the next. And so, the argument I'm going to try and make here is that in the unsupervised RL setting, what you should be doing is directly modeling the dynamics of the world, which we're going to refer to as model based RL or world modeling, right, often. And so today, let's talk about world models, right? So um, the premise is still kind of offline RL, but the transition I want to make is going thinking of offline RL as a method for data driven decision making, and then a good technique for data driven decision making should be unsupervised in a way, and let's talk about world models, right? And so what do I mean by a world model? I mean a predictive model, a learned predictive model of future observations in the world, directly operating from perceptual inputs, right? So something that this is from the original world models paper back in 2018, but it's something that takes in your current observation, some measure of control, and then tries to predict something about the future, right? So typically what you'd have is you have some data set, And that data set is used to learn the parameters of this learned predictive model p hat theta, which take in the current observation OT, take in some actions or control AT, and then try to predict observations in the future OT plus one. Right? So you have observations in, actions in, and future observations out. So you'd often refer to this as action condition video prediction, or video prediction models. And why do we care, right? Like, so we get these things, but eventually you want to act in the world, right? So you want your robots to do things, you want your decision making agents to do things. So why do we care? Um, Now, the reason we care, and companies like Wave and 1X and a lot of others are investing in these world models, is that it's naturally a good way to do planning and decision making. It can accept suboptimal data very naturally. It's naturally off policy. It becomes easier to decide what actions to take, and you can synthesize controllers, and kind of ties into this paradigm that everyone loves right now of test time compute, right? And so, in principle, learned dynamics models enable test time compute. Secondly, it's great as a method for outcome prediction. So if I know that if I take these actions, I'm going to slip off the road, then I can like shield against taking those actions. So I can prevent unsafe behavior. I can like monitor when I'm going to have unsafe behavior and ask for help and so on. And lastly, it's great as a tool for evaluation, right? If I have a great model of the world, I can take two controllers, run them, I can see which one is better. And so I have a much cheaper cycle of evaluation for any AI system, right? So I don't have to go and deploy a controller in the world. I can evaluate it offline. And so world models should be really useful, but let's see what might make learning them quite challenging. Right. So some preliminaries here we're going to say are we'll follow the typical MDP, POMDP type formulation. We'll have observations O, actions A, rewards R, some transition dynamics. Let's call them P, OT plus one given OT and AT. You don't have access to them, but you can sample from them. And you'll have some initial states, let's call them rho naught, right? Some discount. And the goal here is to, in some ways, maximize the expected sum of rewards. We'll talk specifically about the unsupervised setting, but let's just think more generally about world modeling first, and then we'll specialize to unsupervised. Um, and the premise of learning world models is typically trying to approximate some one-step model of the dynamics of the world via supervised learning, right? So what you do is you take a corpus of data, observations, actions, next observations, and then you try to maximize the likelihood of future observations given past, given past observations and actions, right? So you do some supervised learning objective, and for different choice of this p hat theta form, you get different loss functions, right? So you can have an L2 loss function, a score matching loss function, and you can get different types of expressive models, but they're all kind of boiling down to supervised learning of one step dynamics in one way or another, right? So the nice thing about this is that it's supervised learning. You don't have to do all this fancy TD learning stuff. You don't have to do any like complicated optimization. It's supervised learning, and in principle, it's nice because it's independent of reward. It's easy to transfer, and so on. So the principle of learning a world model, which is like a model of the dynamics of the world, is just supervised learning. Should be nice and scalable, right? And then once you have this model, you can then try and do planning against it, right? So you can say, okay, I have this model of the world. I can generate samples within my model. So I can generate samples within my model. Then I can score the different samples by how good the rewards were, and then use them to pick the best actions to then execute in the world, right? So planning might look something like this. Um, Often you do some autoregressive generation in this. So you start from some OT and AT, you run it through your dynamics model to get O hat T plus one. You run that through a dynamics model again with AT plus one to get O hat T plus two, and you repeat, repeat, repeat till you get a full sequence of observations. You then score your observations, and then you pick the best sequence of actions, right? So planning in somewhere or another looks like this. It doesn't have to literally be planning, it could be policy learning, but whenever you're doing decision making within a model, you often are doing autoregressive generation. So the model generates one step at a time, you autoregressively keep generating things. Hold on. I can't see you guys, so let me know if there's any questions. Okay, good. Okay, so you're autoregressively generating things one after the other, right? And that's kind of how planning looks like in a learned dynamics model. Now, this is great in principle, but often what happens is when you increase the observation size and the horizon, this starts to break, right? So imagine this was your true rollout, like you had a true series of things that you expected. You'd often have your predicted rollout start to deviate from there, right? And so small model errors. So even if your model is pretty accurate, your validation loss is pretty low. You can have small model errors lead to large compounding errors in the long term because you have autoregressive prediction, right? So you can kind of think of it as like your dynamics model takes an observation action, makes a small mistake, and then it goes a little more out of distribution for the policy for the model at the next step, which makes a little bit of a bigger mistake, a little bit of a bigger mistake, a little bit of a bigger mistake until it starts deviating a lot, right? And so in general, autoregressive prediction tends to kind of start deviating from the truth, and this gets worse as you increase the observation size and you increase the horizon, right? And so as you scale the horizon, you can see that like blue and red in the bottom curve kind of like depict um, deviation, and you can see that you start to deviate a lot from the ground truth. And then you start to have things that like look a little blurry, right? So um, I mean, these things have gotten better with diffusion models, etc., but they're still like quite short horizon in the grand scheme of things when you're thinking about decision making. And so you find that these world models still scale poorly with horizons, still scale poorly with observation size, especially as your scenes get more and more complicated, right? And so our goal today is going to be to try and define a class of these kinds of dynamics models, which are reimagined, right? So we want to think about the basic principles of world modeling, but try to think about how to get methods that don't suffer from this compounding error issue. We don't have models that suffer from um, this like scaling poorly um, with horizon and observation size, right? And so what I'm going to try and think about is like how do we reimagine the process of developing a world model conceptually in a way that enables things like planning or outcome prediction or model evaluation in the future, right? And so I want to do that while avoiding challenges like compounding error and ensuring that we can scale with size of observation and horizon. Right. So the logical flow here is that we want to build world models. They scale poorly with observation size and horizon. How do we reimagine the thing from one step observation prediction to something else that still enables planning, still enables outcome prediction, still enables model evaluation, right? And so we want to build models that go beyond this paradigm of autoregressive next state prediction and try to think of new ways of doing world modeling. Okay, so to kind of get at that, I think we have to go to the very core of what we mean by a model, right? And so when I say a model, we typically think of something that looks like this. It's something that takes in your current observation, current image of the world, action, and then predicts your future observation. Right? So that seems like a reasonable way to define a model, but there's a bunch of things that are in this definition, right? So one of them is that it's generative. It's generative of future observations. Second is it predicts things about the future given some control. The third is that because it's predicting one step at a time, it's autoregressive, which means that you generate one step, you go back into the model, you generate one step, you go back into the model. It's inherently one step, you're predicting one step at a time. And lastly, you're predicting observations, right? You're still predicting what the future frames look like. Now, some of these things are good and some of these things are not good, right? So I'm very happy to have things that are generative, they generalize well. It's great to predict things about the future because that enables you to do control. But it's generally bad to do things that are autoregressive. You have compounding error. It's bad to do one step things when you want to predict multi step things. And you never actually need to predict future observation. You usually want to predict something more compact than future observation. Right? So some of these elements are good and some of these elements are bad. And so, what we're going to try and do is retain some of the key elements of a model. And in doing so, we're going to redefine what we mean by a model. It's going to be something that takes in an observation, takes in some measure of control, and then tries to predict something about the future. Right? It's not going to necessarily be the next frame. It's not going to necessarily even be a frame at all. We're going to say we're going to predict something about the future. And then we're going to instantiate a process to do planning under that model. Right? And so We're still going to build things that look like world models. They're generative models about the future, but they're not going to be autoregressive. They're not going to be one step, and they're not going to predict observation, right? And that's still going to allow us to do decision making, but it's going to still avoid these problems that we talked about earlier with, you know, observation dimensionality, horizon, and these kinds of things, right? And so that's kind of the premise here, right? So your control need not be action. Your thing about the future need not be next state or next observation. We're going to try and rethink those assumptions that, you know, people hold as fundamental. Okay, and so what this talk is going to be about is we're going to try and do two things, right? So we're going to say we're going to redefine what a world model is. We're going to change two things. The first is we're going to try and change what we predict. Right now, world models are predicting the next observation as, you know, as the prediction outcome, the next frame. And the second thing is we're going to change how we predict. We're going to change exactly the procedure of predicting, and we're going to change what exactly we are predicting, right? And so the kind of the structure of the talk today is we're going to have two subsections. The first subsection is we're going to talk about how do we deal with large observation sizes by learning from task relevant objectives. And the second is how do we learn models of cumulative outcomes so that we can deal with longer horizon problems. And so the point here is that where the first section is kind of changing what we predict, and the first second section is changing how we predict. Right. Okay, so let's recap. We've talked about offline RL being a science of data-driven decision making. World models are a great way to do unsupervised decision making for from data. Now, if we want to think about world models, they have these challenges of compounding error with state space and horizon. To kind of get around them, we need to rethink the paradigm of world modeling, and we need to change what we predict and how we predict, right? And that's kind of how we got here. Okay, I'll pause for a second. Any questions? Um, I lost you guys. Okay, no questions so far. Good. All right, so let's start by thinking about changing what we predict, right? So, um, when we think about autoregressive prediction in the world model, you take in your current observation action, you predict your next observation, you autoregressively predict. You start to see weird things like this, right? So on the right, you can see that the carrot starts growing magically, right? So you can see weird behavior that looks like this, and you can see like even if you look at the latest and greatest models like Cosmos and whatever else, Runway ML and these kinds of things, like all of them have like elements of unphysical behavior, elements of fuzziness, elements of scaling poorly with observation size, right? And so model predictions often either get blurry or they start to hallucinate, especially in places that are important for decision making. And so the thing we started thinking about is, do we even need to predict the next observation? Do we even need to predict what the future frames are going to look like in terms of the pixels? And so what if we instead made predictions in a latent space, right? So let's say instead of predicting, from observations and actions directly to next observations like we do over here, what if we instead said lifted this whole thing to a latent space? So you go from observations to a latent space, and then you make future predictions in the latent space, which is a more compact space. Right? So this is nice because you're no longer predicting things which is in terms of like future pixels. But and then the nice thing is you can do multi-step prediction in latent space without having to go back to images. So you don't have to go through the process of generating an image, feeding it back in, generating an image, feeding it back in, and so on. The challenge here is like, how do we know what latent space is a good latent space? And so, a natural one that is often used is lossless compression, which is often called reconstruction. Right? So, in reconstruction, you say good latents in the future are able to reconstruct future observations. So, Z1 should be able to reconstruct O1, or Z2 should be able to reconstruct O2, and so on. Right? And so, we're building a model of the world. You still do predictions in latent space, but you ground the latents by using them to predict future observations, right? So this seems easy enough, and this works in many cases, but it can struggle when you have cluttered dynamic environments or you have visual distribution shift. And a way to think about this is because you're trying to reconstruct the whole observation. Let's think about these two examples, right? Like you see, there's so much complicated stuff going in the background. A lot of your capacity for modeling is gone to modeling the background, not the things that matter, right? Same thing in like models like Cosmos and so on. You like generate really nice, pretty pictures, but you don't really capture the things that matter always that well. And so um, it's a nice paradigm to do reconstruction. The challenge is that it struggles with complex, cluttered environments and doesn't really get the things that matter. So we still want to retain, the elements of latent dynamics model. So where we start, we said we wanted to do dynamics prediction, change what we predict. We started by saying, okay, what if we went from observation prediction to latents? And then we're saying that, okay, latents are great, but like, they can struggle to predict the things that matter. So for instance, you can see in these predicted frames, like on the left especially, you're like completely failing to predict the object that matters, which is really that thing in the front, right? And so um, one way to think about this is that models are really important because they enable control. And so the thing that we really care about from a dynamics model, from a world model, is the ability to do decision making or planning with it, right? And you want to predict current rewards and future rewards. If I want to do planning, I need to know how good a sequence of actions are. I don't care about future observations, only I only care about them in the perspective of knowing what the future rewards will be. And so, if you look at all of these things, like you just care about latents that are able to predict rewards, right? So you only care about decision making. And the best way to do decision making is to be able to predict reward. So the proposition we made is that you want to ground a latent space for control, right? You want to ground this latent space. Reconstruction can struggle to capture what matters. So what if you instead have latents that are predictive of, you know, current and future rewards, right? So what that says is that rather than having a lossless compression of state, which just says let's reconstruct the observations, let's have a lossy compression of state. Let's lose information and only retain the information that is allowing you to predict the current reward and the future reward, right? And so the idea that my student Chuning had was we're going to have things that go into latent space, then predict future latents. But rather than going and predicting the observations through reconstruction, you instead want to be predictive of current and future reward. And so the point here is that you're predicting latents, but instead of predicting latents that predict future frames, you predict latents that predict future rewards. And rewards are like they basically capture only the things you need for decision making. Right? And so the nice part is that you're only predicting what matters and you're avoiding reconstruction, which is great, right? Um, the nice part about it is that it like tends to scale with observation size, right? It doesn't matter how big your images are. It doesn't matter what the dynamic backgrounds are. It only matters what the reward is. Right? So essentially, what you're doing is you're predicting future latents and how latents evolve. But latents are predictive of future rewards. And so, if you're able to predict future latents, and from future latents you can predict future rewards, then you can do planning with this system, right? So you can kind of think of it as a world model that operates in latent space and predicts future rewards. If you can predict future rewards, you can do decision making. Okay, so this is great, but what you find is that this objective by itself can still contain some spurious information, contains more information than you need. Right? And um, so essentially, nothing in this objective tells you to drop the information that is not important, right? So you'll often have spurious correlations in the data. So this is especially evident if you look at like these kinds of observations. You see that there's all this like random stuff in the background. Like this, yes, predicting reward is good, but you can also predict spurious correlations in the data, which may not actually matter. And so, a common idea in machine learning is this idea of an information bottleneck. And so, more generally, if you have a prediction problem to go from X to Y, and you have some intermediate representation Z, this is a thing called the Infomax principle, which says that what you want to do is get your latent representation Z to have high mutual information with your output Y, while having low mutual information with your input X. right? So you can kind of think of this intuitively as saying you want to be predictive of your output. You want to be able to like make good predictions, but you want to retain as little information as possible from the input. So you're trying to find the minimal set of information from the input that allows you to predict the output. Right? And so it's a pretty simple principle. It's used all over machine learning. Um, and you can apply this to a sequential data set, right? And so you can apply this to a sequential data set of observations, actions, next observations, and rewards. And so the analog of this information bottleneck principle is going to be this objective, right? So it's going to say, try to find a latent Z, which maximizes the mutual information between the latents and the rewards and minimizes the mutual information between the latents and the observations, right? So you can kind of think of this as something that is predictive of future reward. That's what you can think of mutual information as saying, get Z's that are predictive of future reward. And then secondly, find Z's that are minimal and contain the least amount of information from the input, right? And so that's kind of how you think about it intuitively. Now you can go through some like fancy algebra, and then you can relax this into a combination of two objectives. Like the details of the objectives don't matter as much, but you can kind of think of this intuitively as follows, right? You can kind of think of it as the top objective, which is mutual information over between the latents and the rewards, as saying, let's learn latents that are good at predicting rewards. Right. So you're going to say, if I had a reward predictor QR, I want latents that are able to accurately predict rewards. Right. That's all that you want to think about. And the second objective is saying you want latents that are minimally reflective of observation. And so this one's a little harder to understand, but we'll unpack it in the next slide. But you can kind of think of it as like if you had a prior, which is something that takes in Z and A and predicts future Z, and a posterior, which is something that takes in Z, A, and a future observation, and then predicts Z t plus 1. You want those things to be as close as possible to each other. Right? So we just go through the algebra, but I'll walk through what this means intuitively. So you kind of think of these two objectives as saying, have latents that are predictive of future reward and have latents that are minimally predictive of the input. The first objective just says be predictive of reward. The second objective says make the posterior and the prior as close as possible to each other. And let's try to unpack that objective, right? So essentially what that objective says in words is that try to build models that only predict predictable elements of the world, right? And so, what I mean by predictable elements of the world is that the first objective is going to predict the reward, and the second objective is going to try and predict things that you can predict reliably, right? And so, you can kind of think of this as if you had a scene which had, let's say, a robot and some people, right? So the robot is controllable, people in the background are uncontrollable. Your prior is going to be able to predict where the robot is going to go because you control it, right? But there's many possible futures for where the human could go because you don't control it, right? And so your posterior will tell you exactly where the human is and where the robot is, but it's hard to predict the uncontrollable elements of the scene. So, for instance, if there's someone roaming around in the background of your scene, like it's hard to know how to like what exactly they're going to do, right? And so, what this objective essentially does is it says predict the predictable elements, right? So, predict the elements that are the most predictable, which is the robot arm, but discard the elements that are unpredictable, which is the humans in the background, right? And so, you're kind of encouraging your representation to only model the predictable components. So think about this objective in terms of two parts. One is predicting the rewards, which is predicting what you need for decision making. And two is getting minimality by only predicting the predictable components, right? And so you're combining these two objectives. And so the eventual learning process looks something like this. You have a latent, which learns a prior. You have a prior and a posterior. You kind of try to make those as similar as possible to each other. And then you have a reward model that goes from the latent and tries to predict reward. So you try to combine two objectives, learn a latent that is predictive of your reward. So learn the things that matter for decision making. And secondly, is only predict the predictable, right? Okay, so I know we went way into the details, but what did we do, right? We wanted to change what we predict. We didn't want to predict future observations. So if you notice in this objective, nowhere are you predicting future observations. There's no reconstruction. You're you have a model now that's predicting latents and future latents, but you're predicting only the things that matter for decision making, and you're discarding things that are unpredictable in the environment, right? And so by doing so, you're predicting the minimal set of things that you need for decision making. And so you can then optimize this with any standard procedure. But the key idea here is really you can kind of sum it up through this gray box here. You want things that are predictive of rewards, but are only predicting the predictable elements. Right? And so if you go back to original motivation, we're trying to say predict the elements. Like you don't care about predicting future observations. You only care about predicting latents that are good for decision making and predicting the predictable. That's it. Okay. So, does this work, right? So we tried this on a couple of different tasks in simulation and some robots in the real world. And so a few different findings that we had, right? When you have these dynamic environments, the things with lots of stuff going on in the background, you can see that uh, this method, which we called resilient posterior optimization, right, is shown in orange, tends to do a lot better than methods for model-based RL or methods for representation learning. Why it works well is kind of represented through this probe at the bottom, right? So you can see that it reconstructs the objects reasonably well, but kind of like messes up at getting the background, right? So it like focuses on the thing that matters more than the thing that is unpredictable, right? And that's kind of what leads to better performance. And so you learn a task relevant representation and you kind of ignore the dynamic distractor elements which are not controllable or not predictable. The second thing we tried to study is, does this kind of method learn in dynamic environments? So we had this robot running around in this room, and there's this classic problem in control called, or reinforcement learning called the noisy TV problem. So if you look, there's like a screen which is playing YouTube videos in this room all the time, right? And so a classical method which is trying to reconstruct observations is going to struggle when you have a video playing screens all the time because it like focuses on that. But if you ignore that, you can see that you get significantly better performance, even on a robot in the real world, in dynamic scenes. Um, and lastly, can we learn across diverse environments? So, like, let's say you had environments with lots and lots and lots of different backgrounds, or environments with lots and lots and lots of different tasks. You see that this repo method tends to still learn very effectively, and you can kind of understand this by looking at like a TSNE plot or like a visualization of the representations. And you can see that the representations learned by this kind of minimal method are in orange, while the representations learned by reconstruction method are in blue, right? And so the point being that different methods which are or different scenes which look pretty different but are functionally the same are mapped similarly with this method, but mapped pretty differently with standard world modeling, right? And so you're able to enable better asymptotic performance across environments because you're sharing a lot more data. Okay, so let's skip this one and let's zoom out, right? So the key point that I want to convey is that, okay, we started from offline RL, we said we want to do world modeling. World modeling currently models future observations, but that's doesn't scale well with observation size. It's more than you actually need for decision making. So the argument here is that world models don't need to predict future observations, but instead they need to predict task relevant entities. So they need to predict things like latent representations, which are representative of things that matter in the world, right? So we introduced this kind of like information bottleneck approach to do this, and essentially what it boils down to is representations that are predictive of current and future reward while minimally predicting things that are unpredictable, right? And so essentially you're changing what to predict from just predicting future frames to predicting just the things that are necessary for decision making. Okay? So that kind of defines a new style of world models, right? So world models that are focused on decision making. Okay, I'll pause here again. Any questions? Okay. I don't see any yet. Um, okay, so now we've talked about a new style of world modeling, which is trying to predict rewards, right? Let's think about a second challenge, which is saying we've changed what to predict. Let's kind of change how to predict from here, right? And so, this model that we still talked about is still an autoregressive prediction model. It's an autoregressive prediction model in latent space, but it's still autoregressive. So you're going into latent space, you're predicting the next latent, you're feeding that back into your model, you're predicting the next latent, you're feeding that back into your model, and still you're still doing this generation process of generate feedback in, generate feedback in, generate feedback in, and repeat, right? And so it doesn't really eliminate the problem of compounding error. So you still have this problem of quickly deviating from the ground truth, right? And so this becomes a problem as you go to longer and longer and longer horizons. And so any of these learned dynamics models, even if you're just predicting these latent variables, are still prone to compounding error. Now, what we're going to try and do in this subsection is we're going to try and change the class of models themselves in order to avoid autoregressive generation. And so, what I mean by that is that right now, models are predicting one step at a time. So, you're saying, let's take into current observation, let's predict the next observations, or let's predict the next latent. Right? Um, but they're still predicting one step at a time. And the question we asked is, what if we, instead of predicting one step at a time, directly modeled long-term outcomes? So, you want to take in your current observation, then some element of control, and then predict not just the next step, but what is going to happen over many, many, many steps in the future, right? And so, what we want to do is we want to think about ways to model the long term future in order to avoid compounding error, right? So, compounding error comes because you make a little mistake, you feed that little mistake back in, make a bigger mistake, you feed that bigger mistake back in, you repeat, 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 and it gets worse, right? But what we want to do here is kind of directly model cumulative long-term outcomes so that we avoid this kind of problem. So directly model what is going to happen over 100 steps in the future or 1,000 steps in the future. Right? Now, so one method that tries to do this is what you call model-free off-policy reinforcement learning. So it's what you refer to as Q learning in a lot of your lectures, right? So Q learning or actor critic method, soft actor critic, all of these are model-free off-policy RL methods. And what model free off policy RL does is it essentially alternates between two processes. The first one is a policy evaluation process, and the second is a policy improvement process. Right? So policy evaluation is kind of the process of minimizing the Bellman error, if you remember this from your lectures, right? Um, and the policy improvement process is saying, let's try to find a policy that maximizes the Q function. So you have a Q function, which is defined here as the expected sum of rewards in the future, starting at some state S, taking an action A, right? You get this Q function through policy evaluation, minimizing the Bellman error. And once you have a Q function, you can improve your policy by choosing a policy that improves your Q function, right? And so most of these kinds of off policy model free RL methods are going to take this kind of form, right? And the nice part about it is that your Q function node is not autoregressive in that yes, you're doing dynamic programming at training time, but at test time, you're directly predicting the cumulative outcome. You're not predicting one step at a time. You're predicting the cumulative outcome all at once. And that kind of allows Q functions to have a lot better performance over long horizons. And so if you look at any of the model-based RL methods, they all have a value function somewhere to shorten the horizon because value functions just work way better over long horizons. So model free off policy RL is nice because it can directly predict things over long horizons. So it might be a solution to kind of our challenge of avoiding this kind of autoregressive prediction. Right? So you want to avoid one-step prediction. You want to directly predict cumulative outcomes. Okay, so we wanna think about how to use ideas from model free off policy RL to kind of build a new class of world models. Right now, model free off policy RL is great, but Q functions are not unsupervised, they're not general purpose. Q functions represent the sum of rewards under a particular policy. So if you look at the definition of a Q function, the Q function, right, this is the standard definition of a Q function, which is it's the expected sum of rewards in the future, starting at some state S, taking an action A, but acting under this policy pi, right? So you're saying it's specific to a particular reward and it's specific to a particular policy. So it's predicting the cumulative outcomes, but it's predicting the cumulative outcomes for a particular controller and for a particular task, right? And so Q functions have lots of similar properties to models. They're predicting things about the future, they're predicting the cumulative outcomes, which is great. But Q functions depend on reward and Q functions depend on policy. So if you go back to our original motivation of like having an unsupervised corpus and just training one thing that can quickly be used on many different downstream things, Q functions don't satisfy that directly, right? Because they're dependent on reward and they're dependent on policy. So you train a Q function for one reward, it's not going to work for another reward. You train a Q function for one policy, it's not going to work for another policy, right? And so it's hard to use it directly, but we're going to make a few changes to this framework, which is going to allow us to use it for this problem of world modeling. But it's going to allow us to do it in a way that generalizes to new problems while modeling the cumulative outcomes over the future. Okay? And so the question we're going to ask is how do we build models without autoregressive next step prediction? And essentially that question boils down to how do we build off policy reinforcement learning methods, so things that look like Q learning but remove the dependence on rewards and remove the dependence on policies. Right? So how do we build Q learning type entities that are good for unsupervised RL, unsupervised prediction? Right? And so my student tuning had an idea he called dispose. But dispose is the key idea is you're trying to use TD learning, temporal difference learning, Q learning, to model cumulative outcomes in the future, but do it in a way that's independent of reward and independent of policy, which means that you want a model that you can use to evaluate arbitrary new rewards and you can use to evaluate arbitrary new policies. And if you can do that, then you can solve new tasks. Right? And so you can kind of think of it as taking the ideas from Q learning, but changing out how you depend on rewards and changing out how you depend on policies. And so there's two sections we're going to talk about. The first is how do we get things that are independent of reward, and the second is how do we get things that are independent of policy. Okay. And the result here is a new class of world models that look more like Q functions. They look more like value functions, but they allow you to enable transfer without having all of this compounding error problem. Right? And so that's kind of the key idea here. So let's start by thinking about reward independence, right? So we want things that look like Q functions, right? So Q functions look like this. They're expected sum of rewards in the future, but we want to make them independent of reward. And so the Q function definition depends on a particular reward. The simple thing we're going to do is what if we replace the reward R with some vector valued function G? Let's not worry about what it is for now. Let's say you replaced Q by some vector valued function G. Normally, reward is a scalar, which means Q is a scalar, but you can do the same definition with a vector valued function G and a vector valued Q function, let's call it psi, right? So this is exactly the same definition as a Q function. You're saying is the cumulative sum of these features G, and we're going to call G our cumulant, and we're going to call psi um, like our feature, our cumulative features, right? So you can say that psi pi is the cumulative sum of features in the future, starting at some state S and taking action A. So it's exactly the same as Q function for rewards, but you're replacing R with G, right? And so the only thing you're doing is you can train with the Bellman error, everything remains the same. It's just vector valued rather than scalar valued. Now, why does this matter, right? So why we took our Q function, we replaced R with some arbitrary G. This is nice because G is not specific to any one problem, right? G can be an arbitrary feature and it's not specific to any one problem. And this kind of allows us to transfer across tasks. So the key insight behind this idea called successor features, which is from prior work, is that if you can show that rewards are linear in G, then Q values are also linear in psi, right? So you can show that if rewards are linear in G, you can show that Q functions, the actual Q value, the cumulative sum of rewards are linear in psi with exactly the same coefficient, right? And so what that means, like the details are less important, but really what that means is that all I need to do in order to make these Q functions agnostic to rewards is I need to model not just a cumulative reward, but I need to model a cumulative feature, a cumulative g function, right? And then once I solve a linear regression problem saying that like r is equal to some linear function of g, I need to figure out this coefficient w. But once I have the coefficient w, I instantly get a q function, right? So all that I need to do for a new task is solve a linear regression problem, and then I instantly have a q function. So transfer to new problems is just linear regression, right? So let's skip all this. But really, what this means is that um, instead of modeling a cumulative reward, let's model a cumulative feature. Let's call that psi. And once you have psi, getting new Q functions is as simple as solving linear regression for rewards and then instantly getting the Q function for new rewards, right? And so transferring to new tasks is as simple as doing linear regression, which is really easy. Right? So the key insight here is that instead of modeling rewards for a particular task, model some cumulative random features. Let's call them G. And then once you have these cumulative features, you at test time you can just solve a linear regression problem, and you instantly have Q functions without having to redo anything else, just linear regression, right? So the insight here is that rather than modeling the Q functions of rewards, model the Q functions of random features. Once you model that, you've reduced transfer to linear regression, right? So that's the key insight here. So if you want to make Q functions independent of reward, follow this insight, model the Q functions of random features rather than particular rewards. But there's still a problem. Like Q functions, by definition, if you look at this definition of cumulative features, it still depends on the policy pi, right? So it's still saying like, what is the sum of features in the future, starting at some state S, taking an action A, and then following this policy pi, right? But for different tasks, you'll have different pies, right? So let's say you have a robot navigating to two different places. The policies that you're going to run are different for both of those. And so what you need to do is you need to have a method that is not just evaluating things for new rewards, but is also being able to evaluate things for new policies, right? So we built this new class of world models, which can evaluate things for new rewards, but we also need to be able to evaluate things for new policies. And so the problem is we don't know which policy is going to be evaluated a priori. You just have this corpus of data. Nobody's told you what policy is going to be used at test time, right? And so the question is, how do we eliminate the dependence of a Q function on a policy? So the problem is if we don't know what policy needs to be modeled or evaluated, we just evaluate everything, right? And so one way of thinking about it is that rather than you can let's call this like this function psi an outcome distribution or an outcome function. So it's saying that if you have a vector valued function g, psi is a sum of that vector valued function g over time, right? So it's essentially saying what is the cumulative feature over time, but it's for a particular pi. We don't know which pi is going to come. So let's just model the distribution over all possible pi's, right? So let's say you had a simple four-state MDP. You started at S naught. The features are shown here as G naught, G1, G2, and G3, right? And you had like two paths in your data, right? S naught, S1, S3, and S naught, S2, S3. We don't know which path is going to be evaluated at test time, right? So what you're going to do is instead of modeling just one of the paths, you're going to model the distribution of outcomes over all possible paths, right? So like at S naught, you're going to model both the distribution of outcomes going from the top and from the bottom, right? And so in order to become independent of policy, the key insight is that you want to model the distribution over all possible things that could happen in the world, right? And so let's say that your future outcome for a particular policy was psi pi. You want to model a distribution over psi pi for all possible things in the data set, right? And so you can kind of think of this as if you want to avoid dependence on a particular policy, you go from modeling like a vector to modeling a distribution over vectors, right? And so you can kind of think of this psi as corresponding to a single outcome, a cumulative outcome in the world, which is like the sum of features. And P of psi tells you what is the distribution of all possible psis in the data set, right? And so If you have such a data set, you can kind of think of there's two different paths. You can go S naught, S1, S3. So your psi is going to be G0 plus G1 plus G3, which is going to be 0, 0 plus 1, 0 plus 1, 1, which is going to be 2 comma 1, right? And your second path is going to be S0, S2, S3, which is going to be 0, 0 plus 0, 1 plus 1, 1, which is going to be 1, 2, right? And so essentially, you can think of this as modeling a bimodal distribution of one peak at 2 comma 1 and one peak at 1 comma 2, right? So it's kind of modeling intuitively, like zoom out from the details. It's saying that you want to have a world model, that is general. You don't want to predict anything for a particular reward, so you predict these cumulative features. And you don't want to predict anything for a particular policy, so you predict the distribution over all cumulative features, right? And so that's all that this is saying, right? And so the nice part about this is that if you don't, like, why is this good? It's if you don't want to commit to any particular reward and you don't want to commit to any particular policy at training time, it's like modeling the distribution of all possible things that could happen in the world. So if you've heard of the notion of affordances, it's kind of like predicting a distribution of all the affordances. Like, what are all the things that could happen from this state? So we'll skip the details here. You can train this with the Bellman model, right? But essentially, what this results in is rather than modeling a single cumulative outcome for a particular policy, you model a distribution over all possible cumulative outcomes, and you avoid committing to any policies, right? And so you just model everything, right? So you can kind of think of this as like it's a world model that models the distribution over all possible futures, right? And then at test time, you can choose which of those futures is good for you, right? And so the two key ideas here are that you get reward independence by, so you're trying to take a Q function, you're trying to remove dependence on reward and remove dependence on policy. You get reward independence by modeling random features, and you get policy independence by modeling the distribution over all possible outcomes, like all possible things in the world. You try to model all of them, right? And you can train this thing with TD learning, and so on. But that's your new world model. So your new world model is essentially this distribution over all possible cumulative outcomes of random features in the world, right? And so you're not doing one step prediction, you're not doing autoregressive generation. You're predicting cumulative outcomes, but you're still general. You can optimize for any reward. You're still you're still like able to solve for new tasks, right? So the way you solve for new tasks is, let's say you had a original corpus of transitions. You then learn this thing. You learn this like distribution over all possible future outcomes. Let's call this P of psi given S, right? And then you can quickly optimize for new problems, right? But the nice part is that it allows you to avoid compounding error, and it allows you to avoid having to redo something like offline RL for every new problem. And so all you need to do for new problems is solve linear regression. So the process looks something like this. You get a small set of labeled rewards for a new problem. You solve a linear regression problem to give you those weights WR, like we talked about earlier. And with those WRs, you can kind of directly get Q functions. And once you have Q functions, then you can directly get policies, right? And so the point here is that you've kind of reduced the transfer problem to a new setting directly to linear regression, right? So let's skip to this, but the key element of this is saying that you have a new class of world models that are directly predicting cumulative outcomes in the future. This is nice because you're avoiding compounding error. And like normally, if you had to use offline RL for many different problems, you would have to redo the whole TD learning. You have to redo offline RL for problem one, and for problem two, and for problem three, and for problem four. Right? So you have a transfer process that is avoiding compounding error and avoiding redoing TD learning. Right? And the key insights are you directly model cumulative outcomes, you model random features rather than modeling a particular reward, and you avoid committing to a policy by modeling all possible outcomes in the world. Right? And so if we go back to the definition of a model, right? So the model we said was something that takes in an observation, action, predicts future observation, right? um, we've kind of like redefined what a model is by saying that it's something that is generative. It predicts things about the future, but it's not autoregressive. It's not one step, and it's not predicting observations in the future. Right? It's predicting cumulative features in the future. It's predicting the distribution of that over all possible things in the world. And it's like avoiding any autoregressive one-step prediction, right? And so predicting, it's kind of like predicting what the long-term futures are going to be. It's like saying, oh, this could happen, or this could happen, or this could happen, rather than saying, hey, I'm going to predict this future frame, or I'm going to predict this future frame, or I'm going to predict this future frame. So you've kind of removed the process of one-step prediction. You've removed autoregression. You're predicting long-term outcomes in the future. Okay, so kind of complicated, but like the key insight to take is basically this. You're redefining what a model is. You're predicting long-term futures in the environment, or maybe this is actually the easiest way to think about it. You're predicting long-term futures in the environment which are reward independent and policy independent. That's it. Right? The details of these kinds of things will change over time. But the thing I want you guys to take away from these kinds of methods, right, is Q learning or like models don't need to predict next frames. You can predict long-term outcomes, and let's think about new ways to predict long-term outcomes, right? And this is one way, but there's many other ways. Okay, so let's go through some experiments. The important thing in these experiments is to look at, we're trying to say, you have an unsupervised corpus in each of these tasks, and then you solve particular downstream problems, right? So this method is shown here as dispose, right? And then you have methods that are like model-based RL, you have methods that are model-free RL, and you see that you tend to transfer a lot better and deal better with longer horizon problems using this method. And so it tends to do better than model-based RL with longer horizon and tends to transfer better than model-free RL. So when you're thinking about offline RL methods, right, model-based RL offline RL methods will not go well with horizon. Model-free offline RL methods will not transfer to new problems. And this kind of gives you both. The second is that you're able to do new tasks without as much compounding error. So the way to read this plot is you have this robot on the bottom left. It's trying to get to different squares in the grid, and the more blue the color, the better it's doing, right? And so you can see that like a model-based RL method, like it's called combo, tends to like get worse towards the corners because that horizon becomes really large. Whereas like this kind of method does much better with horizon and transfers to many different problems, right? And so you can see that you can kind of visualize the behavior, but the same model is able to then get to any arbitrary problem in the future. So you retain performance across tasks and you scale with Horizon a lot better. And you can also learn arbitrary tasks. So one thing that like my student tuning asked the system to do was to like draw this character UWCS, right? You can also like, you don't have to do only goal reaching tasks. You can do tasks that like obey preferences, like you want to go towards the left or you want to go towards the right, right? So the point is that it's like arbitrarily flexible. So it's as flexible as any reward based method. You can like solve any reward based task with this kind of methodology. So you can optimize arbitrary objectives or tasks in any way. And then you retain a lot of the benefits of offline RL. So you retain all the benefits of stitching and dynamic programming that you talked about in lecture, right? So you learn very, very efficiently. Right? Okay, so what should you take away from these insights, right? So basically, the argument is that off-policy reinforcement learning, things that look like Q learning or TD learning, is actually model-based reinforcement learning in disguise. You have to get Q functions that are independent of rewards and policies. We do this by getting reward independence by modeling random features and policy independence by modeling all possible things that could happen in the world. So what you've done here is you've changed how to predict. Instead of predicting like a one-step thing and doing autoregressive generation, you're directly predicting a cumulative outcome of random features and the distribution of them in the world, right? And that kind of allows you to get things that look like a model, but different in spirit, right? Or similar in spirit, different in details. Okay, so we've talked about these two elements, and the perspective to give you about world modeling going forward is that models only need to predict what is necessary for control, prediction, and evaluation. Like, I think it's misleading to think about the pretty pictures that you see from these like world models that are out in the world, you see on Twitter and here and there. um, the problem is that they look pretty, but they don't actually help with control, which is the thing that matters for things like robotics or decision making. And so I think I talked about two different methods. They're not the only methods, right? But what I'd like you to think about is whenever you're trying to design models or design things that look like world models take in your observation, they take in something about control in the future, and they predict something about the future. But that control doesn't need to be action, that future doesn't need to be next state, and you need to predict what is necessary for decision making, right? So don't predict like everything that you could predict necessarily. Predict what is necessary for decision making, and it'll scale better. Okay, so I think beyond world modeling, if we zoom out one level further, like what is the big problem in offline data driven reinforcement learning, right? To me, the big problem is this data. We've been looking for this data for years and years and years. We don't know where the data is, right? Like people have been running efforts to collect lots and lots and lots of data and starting companies, and those are a good way of doing it, but they're expensive, right? But what I would urge you guys to think about is what is the source of data in the world, and like how do we get this scalably? So some exciting directions I think for future work are learning from cheaper data sources. So things like action-free video, things that are more scalable than collecting data, let's say, on a robot or in a particular environment. Right. So I think leveraging these cheaper data sources well is not a trivial problem. I think it's an important one. Second is data curation and selection. I think we've right now what we do is we take all our data, dump it into the replay buffer, hope for the best, right? But I think in practice, often the choice of data makes a big difference in performance. We've seen this in every other field of machine learning. It's going to be a big problem in reinforcement learning in the next 5 years. And lastly, I think we need to revisit the problems of transfer. So, we in 2017 and 2018, the ideas of meta learning were very popular, quick adaptation, and in large models like large language models and vision models, adaptation has become more of a thing recently. And I think for as you're thinking about world models or decision making um, for RL, like you also want to think about not just RL in one environment, but really about transfer to many different environments. Right. So if I was to give you some perspective, really think about RL from a data-driven perspective. Like the data is the important part, right? And like think about cheaper ways of getting good data. What is good data, and how do we transfer data across problems? Right? So that's how I would think about it. So this is work done by all of these wonderful people. Chuning, my student on the top left, has led most of this. But yeah, that's it. Happy to take questions.
Thank you, Professor. Uh, it was wonderful, and we are open for it. If you have question, please raise your hand, and I give you mic access. We, I think we don't have a question from the students. Maybe they're a little tired, a little tired because
Yeah, two back-to-back talks. Understood. um, you can also feel free to email me with questions offline. No problem.
sure, sure. Uh, sure. I was thinking that the way that we try to do the word modeling with next frame prediction is not the way that our minds works. And I was wondering to ask you what is the inspiration from the mind? What do you know from how our brain works into word modeling, and uh,
Yeah,
how this align to this idea of uh, these two ideas that you present to us?
that's a great point. So I think So we're still, I mean, Ida, who just talked before this, I think is a great expert in this area, but I think we're still unpacking what exactly the brain is doing for decision making. So um, there is some evidence that the brain is making predictions about the future, but there's not necessarily evidence that it's making predictions about reconstructing retinal observations in the future, you know. um, so I think the evidence suggests that there is predictions about something in the future, and so
Yeah,
the paradigm of generative modeling in the future, I think, is very brain valid, if you will.
yeah,
um,
makes sense.
but I think the other piece of evidence that we have is like the existence of temporal difference learning in the brain. So, like through dopamine signals and so on, like there's a correlation often between dopamine signals and temporal difference learning. And so, there's a lot of processes that are reward driven in the brain. And so, I think the right decision making process combines something that is predictive about the future and something that is temporal difference learning. Um, and so I don't know if I have a great answer on the exact combinations, but I think both of those elements are in there.
Yeah, I understand. Thank you. And if there is no other question, we can end this session. Okay, 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 okay. Thank you, Professor. It was really an honor having you with us.
Of course,
And
yeah.
thank you for accepting our invite.
Thanks for
And
the invite.
and I'm so sorry for waking up so early.
No, no, you're
It
good.
was a mistake. I thought
No, you're
The Washington is the thing that I searched. Okay.
good. Thanks for the invite. I enjoyed chatting with you all, and please reach
Uh,
out if you have any more questions.
Sure, sure. Thank you a lot.
Thank you, folks.
Okay. Have a good rest of the day.
You too. See you.